In this video, we want to talk about nucleophilic substitution reaction. Now, a substitution, it means that we are going to have one group. One group is going to be substituted for another. That is what a substitution reaction is. Now, substitution reactions can either occur by SN2 mechanism or SN1 mechanism. So we are going to focus more on SN2 reaction in this video. So I'm going to put here SN2 mechanism. So you may be asking what SN2 stands for. SN2 stands for bimolecular nucleophilic substitution. Bimolecular nucleophilic substitution. Now, this reaction, it involves the displacement of one group, which is known as the leaving group. So we displace a leaving group by a nucleophile. So a leaving group gets displaced by a nucleophile. Now, first we are going to see what a nucleophile is and what a leaving group is. But before we continue, it is also important to know that it is a bimolecular reaction because there are two species involved in the rate determining step. So we say it's bimolecular because we have two species involved in the rate determining step, RDS. Now, if we say the rate determining step, it means the slowest of the steps involved in the reaction mechanism that will lead to the formation of the desired product. So, for that reason, the rate equation is written as R equals capital K, where we have RL, concentration of RL, times the concentration of the nucleophile. Now, the K here is your rate constant. The RL over there is the substrate containing the leaving group. The substrate containing the leaving group. So the R is just the alkyl, and then the L for the leaving group, and Nu is the nucleophile. Lu is a nucleophile. All right. Now I want us to look at what exactly happens when we have SN2 mechanism taking place. So if we take something like 2-bromopropane, no, let's take 2-bromobutane. So we take 2-bromobutane, we are going to have the carbon 2 bonded to the hydrogen, and then we have the ethyl group here, and then we are going to have the methyl group. All right, and the bromine is also here. Now, what is going to happen is we are going to have the nucleophile, Nu. Nu always have the negative charge because he has a lone pair. So it is going to come in here and attack this carbon. Now, this carbon here is partially positive because of the electronegativity difference between the carbon and the bromine. So that gives it that partial positive charge such that the nucleophile gets the chance to attack it. Now, if this happens, we are going to have an intermediate state of the reaction. We have an intermediate state of the reaction where we have carbon bonded to the hydrogen, and we have the C2H5 and then the CH3. Now, in this state, we are going to have the Br going out, and we are also going to have the nucleophile coming in. At the whole transition state will have a net negative charge. So the Nu here is a nucleophile, and then this is a substrate bearing the leaving group, which is Br. So Br there is the leaving group. So the transition state, or we'll say that a partially bonded transition state, partially bonded transition state. Now, what is going to happen at the end of the reaction? Now, once we have the leaving group going off, we are going to have the nucleophile getting attached to the carbon. By this time, something interesting is going to happen. We are going to have the hydrogen here, and then we'll have the C2H5, the ethyl group, and then we also have the the CH3 over here. All right, and remember, we are going to have the Br minus. So what actually happens here is what is known as inversion of configuration. So we have inversion of configuration. All right. Okay. Now this reaction is, we say that it is a concerted process. It is a concerted process because the coming in of the nucleophile coming in and the leaving group leaving occurs simultaneously. All right. So that is what it means to say that it is a concerted reaction or a concerted process. Now, in the transition state, carbon appears to be having 5 bonds, but then it isn't exactly 5 bonds. Now, what happens there is that the carbon there becomes sp2, is sp2 hybridized. So these 3 bonds here, the one bearing the ethyl group, the methyl group, and the hydrogen will have sp2 hybridization. So we have 3 of that, and we also have the p orbital temporarily holding the nucleophile and the leaving group. So the whole thing looks this way. We have the carbon with these 2 bonds kind of lying in the plane, and then we have these 2 moving away. And over here we have the p orbital lying on the x-axis. So that's how we are able to have that configuration. Now, talking about the reason why we have the inversion of the configuration. Now we have the inversion of the configuration to minimize the steric effect, because if we have the ethyl group here and the methyl group here, the electron cloud of this ethyl and methyl group is going to interact with the nucleophile. So once that's happened, to reduce the steric effects, the bond shifts to this side. So you can see that the nucleophile appears to be on the left side here, while at the beginning, the bromine which is attached appears to be on the right. So that is why we have the inversion of configuration. Now, the transition state requires a lot of energy, which means that if we were to draw an energy profile for this, we are going to have the reactants at a particular energy, and then the product will be formed at. So if I call this place B, this is going to be A. So it's kind of like an exothermic process. All right. Now I want us to look at some of the factors that can influence SN2 reaction. Or let me say the rate of SN2 reaction depends on the following factors. Now the first one is the nature of the substituents. Secondly, we can also talk about the nature of the nucleophile. Thirdly, we have the nature of the living group. And we also have solvent effect. Solvent effect. So the question is, how does the substituent affect the rate of the reaction? Now, we looked at the rate equation and we said the rate of the reaction depends on the concentration of the substrate and the nucleophile. And the K here is the rate constant. So how would the nature of the substituent affect the rate of the reaction? Now I'm going to put here some substituents and how they affect the rate of the reaction. So let's look at the halides of alkanes. So let me put here halide rate and class. So CH3, an ethyl group, the rate is going to be like 30 times, and this is a primary class of halide. And if we have CH3, CH2, this is also a primary class, we have the rates to be 1. That's a primary class. And if we have isopropyl, a secondary class, so CH3, 2, CH. This is 0.03 and it's a secondary class. What about tertiary? For tertiary, we have CH3, so a third butyl group. We are going to have 0 for the rate. That means that it is impossible to have an SN2 mechanism where the substituents are tertiary substituents. Now, this is simple because the more we have the size of the substituent increasing, the more steric effect we are going to have. So basically, it is the reaction is more feasible with a primary class alkyl halide compared to secondary and tertiary. All right. Now we also mentioned nature of the nucleophile. Nature of the nucleophile. For the nucleophile, we have very good nucleophile. We have good nucleophile and some that are reasonably okay. So we can talk about nucleophilicity, where we are looking at the ability of the nucleophile to actually act as a nucleophile, or the basicity. So if you have an electron-rich species bearing a negative charge, so if this is the nucleophile Nu with a negative charge, if it approaches a substrate, let's say X, Y, and X being partially positive due to electronegativity difference, Y is going to be partially negative. If the nucleophile comes in here and attacks the X, they will say that it is actually acting as a nucleophile. But then if you have a species like, let me take methanol. So if this is HOCH3, the hydrogen is going to be partially positive and oxygen will be partially negative. If we have the nucleophile coming in, attacking the proton, throwing the electrons to the oxygen, in this case, it is actually acting as a base, since a base is a proton acceptor. So there's this similarity between nucleophile and nucleophilicity and basicity. All right. So what is going to be a good nucleophile and what is going to display basicity? Usually, when we look at taking the halogens, for instance, if you take iodide, iodide will have a higher nucleophilicity compared to bromine, which will be a better nucleophile compared to chloride, compared to fluoride. That means that the higher the size of the nucleophile, the better it is, because for smaller nucleophiles, it is going to act more like a base compared to the bigger one, because in the bigger ones we'll have the electrons being more delocalized. That means they are available to act as a nucleophile. So these are some example of, so this is increasing nucleophilicity. Increasing nucleophilicity. Now, some examples of very good nucleophiles, we can talk of cyanide, Nc minus. We can also talk of sulfide or thiolate, Hs minus. And we can also talk of iodide, I minus. Now, the ones that can be classified as good nucleophile, we can talk of, so good nucleophiles, we can mention OH minus hydroxide, bromide, and ammonia, NH3. So these guys are good nucleophile. And then we also have the reasonable ones like fluoride, chloride. All right. Now, what about the nature of the living group? So I'm going to clean this part. All right, nature of the living group. We have very good living groups. We also have bad living groups. For a good living group, when it goes out, it prefers to stay in the solution as the ion or the anion. So the bad ones will actually attack back, but good ones prefer to stay as ions. Now the solvent effect. For the solvent effect, if you have the nucleophile and there is a correlation with their basicity. That means that it can actually break down in some kind of solvent. So, for example, if you have a protic solvent, for a protic solvent, that means that we have protons available, like H plus. So, if that happens, a solvent like methanol, we are going to have the nucleophile getting solvated through hydrogen bonding. That means that it is going to get coordinated with the protons that are being released. So methanol, ethanol, they are not very good solvents when we need to carry out an SN2 mechanism. All right. So we also have some solvents that can actually help in SN2 mechanism. And this kind of solvents, we'll be talking about aprotic solvents. For aprotic solvents, it means that we don't have protons available. So when we have the nucleophile coming in, it's not going to get coordinated by these protons, and it has a chance to actually act as a nucleophile instead of being a base. Okay, so some example include DMF, acetone, DMSO. These are very good solvents for that favors SN2 mechanism. So I hope this tutorial helps you. Kindly subscribe and watch out for the next tutorial on SN1 mechanism.